Today we're going to go over the Chapter 6 review questions. As normal, we're not going to go over the first one because it's just terms and definitions. So I'm going to start with review question number 2. Question number 2 asks to identify physical or chemical changes, and it has lots of parts to this question. So for A, it tells me a chunk of sodium cut in half. And is this a physical or a chemical change? Well, this is just a chunk of a metal. It's actually a pretty soft metal, and you're just cutting it in half. So you're not changing it. You just end up in the end with 2 pieces of sodium. Since it's still sodium, this is a physical change. B says a chunk of sodium thrown into water. And just a chunk of sodium, I think there's a video added in a playlist for this chapter about it, but it looks kind of like butter and you can cut it really easily. But if you throw it in water, it's highly reactive and it makes this explosion. And the hint in this is it says it's making sodium hydroxide and hydrogen. So in the end, I am actually have a new compound, and therefore this is a chemical change. For part C, water evaporating from a glass. Water going from being a liquid to a gas is a phase change, but as a gas, it is still H2O, and so this is an example of a physical change. For part D, where it says adding soap to oil to make it spread out across the top of water, this is still, you're still left with soap, oil, and water. There's not an actual reaction that happens here, so it's just a physical change. Part E is cooking pancakes. Anytime you're cooking something, it is a chemical change. If you know what you start with, the batter is very different from the pancake that you end up with, and you cannot reverse that back. So this is an example of a chemical change. And then the last one, part F, is that classic volcano reaction where you add solid baking soda to liquid vinegar and it produces a gas and it makes bubbles. And this is our hint here, is it says it's making bubbles. And anytime something is making bubbles like that, other than like boiling and just turning to water vapor, if it's an actual reaction, it is a chemical change. Question 3 gives me the melting point of table salt, which is actually really high. And it's asking us to convert this from Fahrenheit to Celsius. So you can do this using your science app on your calculator. There is nothing wrong with that, but I'm going to walk you through using the equation that the book gives you. Since the book gives you the equation solving for Fahrenheit, and I'm actually wanting to solve for Celsius, you could flip the equation around like I did in the comprehension check to make it solve for Celsius, or you can just put in the data and use algebra to solve it. And so when I put it in for Fahrenheit, what they give me, I put in the 1,474. And now I'm gonna rework this to solve for C. First thing I'm gonna do is I'm gonna take away 32 from both sides. When I take away 32, I get 1,442, and this equals the 9/5 times Celsius. So now I'm gonna divide it by the 9/5 to get Celsius alone. And you know that when you do division by a fraction, you're actually multiplying by the reciprocal for this. So to get C, you're gonna put 1,442 times 5/9 into your calculator. You should get a resulting answer of 801.1 degrees Celsius. Now, when I report my answer for this, I am gonna be remembering significant figures. And for significant figures, I'm gonna be looking at the information that I put into the equation. And so, yes, 32 only has 2 significant figures, but the data that I put into this equation is the 1,474, and it has 4 significant figures. So I wanna make sure my answer has 4 significant figures. Question 4 is another temperature conversion. So this one tells me that daytime temperatures in parts of Australia can get to 40 degrees Celsius, and it's asking me what that is in Fahrenheit. So you can go ahead and do it in your calculator, or pause, try it on your own, and then come back and check your work to mine. Since I am solving for Fahrenheit and I have Celsius, you do not have to rework the problem like you did in the last one. So you're just gonna take your equation, Fahrenheit equals 9/5, and you put in the 40 for Celsius and then plus 32. I would recommend putting your calculator in one motion, but if you do this in one step in your calculator, you have to use parentheses so that you do not mess up your order of operations. And what I mean by that is you would need to put parentheses around the 9/5 and the 40. And then you would add the 32. That gives me an answer of 104 degrees Fahrenheit, and you're gonna wanna make sure you have 3 significant figures in your answer because you're given 40.0. I know I just added that 0 there because I left off the first time. Question 5 tells me that a comet develops a tail when it gets close to the sun. The tail is the result of frozen chemicals on the comet turning into a gas. And what is the word that we use for this process? Well, usually when things go from being a solid, if you think of a piece of ice, it actually goes from a solid to a liquid to a gas. But in this case, it's going from a solid straight to a gas, and it's asking what is that process? And that process or that phase change is called sublimation. We don't see it a whole lot. 2 examples that quickly pop to mind are mothballs, but it's a little ball that turns into a gas slowly, produces a smell that's supposed to keep bugs away out of your clothes. And then the other one would be a carbon dioxide, which is dry ice. Dry ice goes from being a solid to a gas with skipping the liquid phase. Question 6 tells me that I have a gas and it's condensing on a surface, and it's asking if the gas is gaining or losing energy, and is the surface gaining or losing energy. So the best example, I'm still not an artist, is if I have like a cold glass of a cold liquid, so I have my ice cubes in it, and I take it outside or even sometimes inside on a hot day in a very humid environment. So Tennessee, it is very humid. This happens frequently. When you go outside and you have a lot of air or gas in the air, so water molecules floating in the air, what happens is when they get to the outside of your cold glass, they make these droplets on the outside of your glass that is water molecules. And so that is water going from a gas to a liquid, and that is that condensation or condensing that you get. Now, is the water gaining or losing energy in this? Well, this water has gone, or the gas has gone from being the gas phase to a liquid phase. So in the gas phase, particles are moving around a lot and they have a lot of energy and they're kind of bouncing around and they're really far apart. But as they go to a liquid phase, they actually have to get closer together. That condensing is actually getting closer together and taking up less space. And as that happens, they have to lose energy. Now what's happening on the surface is actually absorbing that energy. So the gas is losing energy and the surface of my cup or my glass is actually absorbing the energy. And eventually what will happen is your ice is going to melt because it's absorbed energy and your water is going to get warm. Question 7 asks, how does sweating cool the skin? And it's kind of confusing sometimes to think of sweating as a cooling process because you're usually sweating on really hot days or in hot situations. But your body sweats to cool you down. So if this is your layer of skin and you're producing, these are like little beads of sweat, what happens is as you produce this beads of sweat, the sweat is able to absorb energy from your body. And as a liquid absorbs energy, its molecules start to move more and they get more energy and they bounce around and they turn into a gas when it is evaporating. So as your sweat is evaporating, it's taking energy from your body and that is cooling you down. When your sweat evaporates, as it's taking your energy from your skin, it's cooling you. If you live in a really humid place where there's already a lot of moisture in the air, it's a little bit harder for your sweat to evaporate and you're not gonna have as cooling of an effect. Question 8 is kind of the opposite of an experiment that you do in the class. So in class, you're gonna do an experiment, or you ought to do an experiment where you take a thermometer and on the bottom of the thermometer, you're putting a liquid, water or alcohol, and you're watching the temperature of the thermometer as you put the liquid on the thermometer and as it evaporates. And as it evaporates, you should see the temperature go down because just like sweat evaporating cools your skin, as the sweat evaporates or as the water evaporates off the bulb of the thermometer, that liquid has to gain energy to evaporate, and so it's pulling energy out of the thermometer and you see the thermometer go down. Question 8 is a very similar situation, but the opposite. It says, suppose you've got a thermometer and instead of gas evaporating off of it, it is actually condensing onto the thermometer. What is happening to the temperature? Is it decreasing, increasing, or staying the same? So gas particles have a lot of energy. They're far apart, they take up space, and they're bumping all around into each other. But as they come into a liquid, if it's condensing on the liquid here, those energetic particles are having to get a lot closer to each other. And as they pull in closer to each other, they are losing energy. And so as they lose energy, some of that energy is actually going to go into your thermometer and you're going to see the temperature increase. So as the liquid condenses on the bulb thermometer, you should see an increase in temperature. It will be very slight, but it should happen. Question number 9 is trying to trick you. It says the temperature of one liquid is at 115 degrees Fahrenheit. The temperature of another sample of the same liquid is at 70 degrees Celsius. And the question is asking you which liquid's molecules are moving faster. Now, molecules are moving faster if they're at a higher temperature. So most students instantly look at this and go, this one is moving faster, it has a higher number. But we have Fahrenheit and Celsius, and so we cannot compare those. So you need to put one of these measurements into the other. So you either need to turn this one to Celsius so you can compare two Celsius numbers, or this one to Fahrenheit so you can compare two Fahrenheit numbers. I would recommend turning Celsius to Fahrenheit because we would already have our equation in this one, in this layout. We wouldn't have to rework the equation. It's already set to solve for Fahrenheit. So you're just gonna do the 9/5 times 70 plus 32. Just remember, if you do it in one motion in your calculator, to use those parentheses. You should get 158 degrees Fahrenheit. So if I was to compare 115 degrees Fahrenheit to 158 degrees Fahrenheit, the 158 degrees Fahrenheit is going to have much more energy. Question 10 is referring to a lab that I hope you did, that I did not talk on this subject on the comprehension check questions, but it says the chemist add 12 milliliters of alcohol, that's supposed to be an and sign, and 11 milliliters of acetone. Acetone is like nail polish remover. And what is going to be the final volume? Your book has a section where it talks about masses adding. So if I have 10 grams of something and I add it to 10 grams of another chemical, I'm going to have 20 grams at the end because we have conservation of mass. Mass stays the same. But volume is not the same way. Volumes don't add up that way. It's a really kind of a weird concept. But there is a experiment in the book where you take a sample of alcohol and you measure it to water. I think it's like 50 milliliters of alcohol and 50 milliliters of water. And you would think 50 plus 50 is 100. But you do not get 100 in the end. You get a little bit less. Because as the alcohol mixes, it can actually mix down into the water and fit between the water molecules. And so it takes up less volume. So volumes are not additive is what we say. So the question is asking what would be the final volume? Well, if I was just to take these and add them up, I would think 11 plus 12 would be 23. Now, I know that the volume is not going to increase, but the volume is actually usually going to decrease. So a good answer of what would be the result would be 22 milliliters. And you can try that experiment. It's pretty easy to do with some pretty basic tools. Question number 11, I'm just gonna add the chart up above. It's a heating curve. And this one kind of makes me laugh because the author of this book is Dr. Wile. And so he kind of used his name for this one. He makes a heating substance or a heating curve up for an unknown. And he says it's a sinister substance and he calls it Wilenium, as I'm guessing how you would say that after his name. And so for this heating curve, we're asked to analyze this graph. What is the temperature? Does it melt? What temperature does it boil? And at what phase is it in at 80 degrees? So if you'll remember at this first part of the heating curve, when a substance first starts, it is solid. And so it goes from being a solid to a liquid to a gas as it gains energy as it moves across this heating curve. So energy is going increasing this way. And so the substance is going from being a solid to a liquid to a gas. So this first little hump you're gonna see is as it's going from a solid and then it turns to a liquid, it levels out. That first little level, you're gonna see it at 20 degrees Celsius. And the whole time that the substance is at 20 degrees Celsius, it is melting. Any energy going into it at 20 degrees Celsius is used to melt Wilenium. Now, once it is at a liquid and we keep having energy, you see a bigger hill go up, and that is going up from the 20 to the 110. But once you get to 110, it levels out and we have another phase change. Anytime it's level, we have those phase changes. So it is changing from a liquid to a gas at 110 degrees Celsius. The question C says, what phase is Wilenium in at 80 degrees Celsius? So at 80 degrees Celsius, you actually are on a slope. It's at that slope right in the middle and it's going up. And so we are right between the melting and the boiling. And so what is between something once it's melted before it boils? So at 80 degrees, it is a liquid. Question number 12 gives me two situations and it's asking which one is most like water. So the first one, it says solid iron sinks in liquid iron. And the second is solid silicone floats in liquid silicone. And this is using water, is comparing it to water because water is weird. It doesn't follow all the rules when we're talking about kinetic molecular theory. If you remember when we talked about kinetic molecular theory, we talked about as something goes from being a liquid to a solid, the molecules actually lose energy and they get closer together. Well, if that happens and the molecules are closer together, the solid is more dense than the liquid and technically should sink. So that is what's happening here in iron. But water is totally different. It doesn't really follow those rules. As it freezes or turns solid, it actually forms something called hydrogen bonds that we'll look at later on in the book. But that allows water as it freezes to expand. And so that is why your ice cubes float to the top of your glass, and when water freezes in a pond in the winter, the ice is on the top and not on the bottom. And so the one that is close to water is this silicone because the silicone is floating. Question number 13 is going to give you a balanced chemical equation, and it's asking you to label the reactants and the products. And so the reactants are both compounds that are on the left side of the yield arrow. And the products are both compounds that are on the right side of the arrow. Question 14 has 5 parts, and each of the parts is asking you to write a balanced chemical equation. And so the first part is writing the equation, and then you're going to balance it. And so these problems feel a little intimidating at first, but you just have to take the words that they give you and break it down step by step. So for 14a, the first thing it tells me is solid zinc. So I'm going to start with solid zinc. It tells me it's a solid. Zinc is not a homonuclear diatomic, so it is not zinc 2. Then I'm told that it reacts with liquid hydrogen monochloride. Hydrogen monochloride. So hydrogen, and then mono means just one chlorine. Remember, these are both nonmetals, so this is a covalent compound. And it tells me it's a liquid. The next part of the problem, it tells you it makes solid zinc 2 chloride, and the 2 is Roman numerals in parentheses. So I have here a metal and a nonmetal, so this is an ionic compound, and so I have to balance the charges as I make this compound. The first part is zinc, and the second part is chloride, and since I know zinc has a charge of +2, I now need to know the charge of chloride. And if you'll look on your periodic table, it's in the group 7, and you should have written above it that those have a charge of 1 negative. Now, I need to balance these charges out, and so since I have zinc with a 2+, I need chlorine to have a total of 2 charges. So I'm going to do that by getting 2 chlorines, and if you'll remember that crisscross method, where you bring the 2 down and the 1 down. That's how you would write zinc chloride. Tells you it's a solid. And the other product that you make is gaseous hydrogen. And I hope you recognize that hydrogen is a homonuclear diatomic. It's never alone, so there's going to be 2 of them. The next step is to check to make sure it's balanced. So for the reactants, I have 1 zinc, I have 1 hydrogen, and 1 chlorine. And over here I have 1 zinc, 2 hydrogens, and 2 chlorines. And so the zincs are balanced, but the hydrogens and the chlorines are not. So I am actually going to balance the chlorines first. The reason is I leave any atoms or elements that are alone to balance last, and hydrogen is by itself, so I'm going to balance it last. So let's do the chlorines. So I have 2 here and I need 2 here. So I'm going to put a 2 there. This gives me here 2 chlorines, but it also gives 2 hydrogens. And so by balancing that out, I now have a balanced chemical equation. So for 14 part B, they actually give you the equation, so you don't have to find it from the words. And it's aluminum, and I'm reacting it with this iron oxide to make aluminum oxide and iron. And I hope you'll kind of start to recognize that what's happening in this equation is aluminum is pushing iron out, and so this is a single displacement reaction because you have one metal pushing another metal out of a compound. So let's balance this. So here we have 1 aluminum, I have 1 iron, and 1 oxygen. But on this side, I have 2 aluminums, 1 iron, and 3 oxygens. So what I'm going to balance first is I realize that I have aluminum alone, so it'll be easy to manage at the end. And the same with iron. Since there's an iron alone, it'll be easy to manipulate at the end. So let's first look at the oxygens. So on this side, there's 3 oxygens, and on this side, there's only 1. So we need it to be a 3. So if you put a 3 there, now not only do I have 3 oxygens, but I also have 3 irons. Now I can go ahead and I can balance out either the aluminum or the iron. So here I have 1 aluminum and here 2. So I'm just going to put a 2 here. That gives me 2 aluminums. And for irons, I'm going to put a 3 here, and that gives you 3 irons. For 14C, we're back to those word equations that we have to make the actual formulas from. And so it tells me calcium is the first thing. And so I'm going to start with my first reactant is calcium. And it doesn't give me a phase on this, so I'm just going to not add it because it doesn't specifically tell me. It's telling me, though, it's reacting with aluminum chloride. The way it has written aluminum chloride, you do have a metal and a nonmetal, so it is an ionic compound. But you do not have those charges in parentheses in the middle. And so because they're not there, I know that this is not a transition metal. It's on either side of the periodic table. And you can go and look up what the charges are. And so chlorine is in that group 7, almost all the way to the very end. And it has about a charge of 1 negative, and aluminum has a charge of 3 positive. And I hope you've gotten that written on your periodic table. Now these charges are not balanced out, so this is not a balanced compound. So we're going to do the crisscross technique to make a balanced compound. 3 negative ones would make a -3 total charge, and that will balance out the +3 on aluminum. The first product that they give you, they say it's calcium chloride. The same thing, we do not have a charge in parentheses in the middle, so it's not coming from a transition metal. Calcium is in the second group if you're on the left of your periodic table. I guess I should have left my periodic table up there. And so it has a charge of 2+, and chlorine has a charge of 1-. And so we're going to cross those charges again, and you get CaCl2, and I'm leaving the 1 out because it's an understood 1 there. The very last product that they tell you is aluminum. Aluminum is not a homonuclear diatomic, so it can be alone. The next step is to balance it, so we have to write down how much of each element we have. So I have 1 calcium, 1 aluminum, and 3 chlorines. And over here we have 1 calcium, 1 aluminum, and 2 chlorines. So to balance at the very end, I'm actually going to leave these calciums and aluminums to the end because they're all alone. And so the other thing left to balance out is chlorines. Now it's a little tricky here because I have 3 and a 2. And I can't multiply 1 like I cannot multiply the 2 to get it to 3. But I can get both of these to 6. So if I wanted 6 chlorines here, since each atom has 3, I would need 2 atoms. 3 plus 3 is 6. That gives me a total of 6 chlorines. Now down here, each atom has 2 chlorines, so I'm going to need 3 atoms to have a total of 6 chlorines. Now this messes up everything else, so now I have 2 aluminums, and this also gives me 3 calciums. So now you're going to go ahead and balance those calciums. So since we have 3 here, and I need 3 here, it's really easy to put a 3 in front of that one, and it doesn't mess any other molecules up. And the same goes for aluminum. I'm just going to simply put a 2 here, and that means I have 2 aluminums, and this is my balanced equation. 14 part D is given to you not in words, but as they already wrote the equation out. And for each of the reactants and the products, we actually have 3 atoms this time. We have a hydrogen, phosphorus, oxygen, and chlorines that we need to balance out. So I'm going to go through and fill all this in. Try it yourself and check to me. 3 hydrogens plus this one makes 4. So we have 3 hydrogens plus 1 makes for 4. 1 phosphorus, 4 oxygens, and 1 chlorine. That's in the reactants. So in the products we have, as far as hydrogen goes, we have 2 hydrogens, 1 phosphorus, 1 oxygen, and 5 chlorines. So now you're gonna look to see what you're gonna do last. And it's really hard on this one because you don't have any atoms by themselves. So what isn't balanced are my hydrogens, my oxygens, and my chlorines. You can really start wherever you want. So I need 4 hydrogens over here. So since each molecule has 2, if I put a 2 in front of it, 2 times 2 is 4. This also changes my oxygens to 2. Now, what else is not balanced out are my oxygens and my chlorines. And so here I have 4 oxygens, and over here I only have 2 oxygens. It's kind of gonna have to start messing with it. So I need to get 4 oxygens over here. Well, to get 4 oxygens over here, I'm really gonna end up changing this too, right? Because if I change this to 4, that gives me 4 oxygens, but that also changes my hydrogens to 8, and they're not balanced. So I'm gonna quit messing with hydrogens and oxygens, and I'm gonna look for something else I can balance. And I quickly see I can easily balance these chlorines. So where I have 5 chlorines over here, I need 5 over here. So I'm gonna add 5 there. That gives me 5 chlorines. Now this messes with my hydrogens. So this means I have 5 hydrogens here, plus these 3, so 5 plus 3 is 8. So that actually balanced out the hydrogens for me. And everything else is balanced out. So this one's a little tricky. You just have to kind of play with it for a little bit. For E, they give you the problem already, but it has 4 parts. I'm gonna go ahead and write out. So I have 2 carbons and 3 hydrogens, 1 chlorine, and 2 oxygens. And in the products, you have 1 carbon, and you have hydrogens in multiple parts. So you have 2 plus 1, so we have 3 hydrogens. And for the chlorines, we only have 1. And we also have oxygen in multiple products, so we have 2, so we have 3 oxygens. So I'm going to leave oxygen for the end because oxygen is by itself and I can manipulate it alone at the end of solving it. So let's look and see what we need to balance first. I'm gonna go ahead and start with carbon. Carbon's always a good place to start. Here I have 2 carbons and here I have 1. So I'm gonna put a 2 here, which will give me 2 carbons, and it also changes my oxygens. So 2 times 2 is 4, but I can't forget this one down here, so there's a total of 5. Now my hydrogens are balanced out and my chlorines are balanced out. So the only thing left is oxygen, and I have 2 and I have 5. So I want to get to a total of 5. Well, what number times 2 makes 5? Well, this is that problem where you do a half, and 2.5 times 2 makes 5. But the problem with this is that coefficients have to be simple whole numbers. And so to get rid of this half, I'm going to multiply all my coefficients by 2. So this, instead of being a 1, becomes a 2. And 2.5 times 2 becomes a 5. This becomes a 4. This becomes a 2. And this becomes a 2. So for question 15, we are once again still writing balanced chemical formulas. We're just going to have to use your knowledge of the types of chemical reactions. So for 15a, it tells you to write the formation of CaCO3. And a formation is the reaction where you have different parts and you mix them together to make a compound. So this is the product. And I need to take apart the product into its parts to see what I have to add up to equal it. So it has a calcium in it, I have a carbon, and I have an oxygen. Now, a big mistake that I see over and over again is people like to say, well, there's 3 oxygens here, I'm gonna add a 3 there. But this is not how we're gonna write oxygen here. This is actually a compound called ozone that's high up in the atmosphere. And oxygen, as is in our gas, and we've learned it's a homonuclear diatomic, you're gonna write it as O2. And so therefore, this is not a balanced chemical equation. We get to balance it. So on my reactant side, I have 1 calcium, 1 carbon, and 2 oxygens. And on my product side, I have 1 calcium, 1 carbon, and 3 oxygens. Now, since one side I've got 2 oxygens and one side I have 3, it's really hard. You cannot multiply it by a whole number to get 2 and 3. Like I cannot turn 2 into 3. But I can make these each have 6 oxygens. So I'm going to do that by putting a 3 here, and that gives me a total of 6 oxygens. And if I put a 2 here, because each molecule has 3 oxygens, so if I have 2 molecules, I will have a total of 6 oxygens. But it's still not balanced, because when I added this 2 here, I made myself have 2 calciums and 2 carbons. But you can very easily start with 2 calciums. You just have to put a 2 there, and you got to put a 2 in front of the carbon. And this is the balanced chemical equation. 15b wants you to get practice writing a decomposition reaction. It tells me I'm decomposing K2CrO4. And so this is actually your reactant. In a decomposition reaction, you take one compound and you break it up into its parts. So what makes this up is potassium. You're gonna want to put a 2 here. Potassium is not a homonuclear diatomic. It exists by itself naturally. Then we have chromium. And the last atom we have is oxygen. And people normally want to put a 4 here because there are 4 oxygens, but oxygen exists as O2. Hope we're remembering that now. And so this would be the decomposition. So let's go ahead and balance it. So on the reactant side, you have 2 potassiums, 1 chromium, and 4 oxygen. And on the product side, we have 1 potassium, 1 chromium, and 2 oxygen. So we're gonna have to do some balancing. As to what we balance first, I don't really think it matters. So here we have 2 potassiums, and over here I'm gonna need 2 potassiums. Then on this side I have 1 chromium, and then I have 1 chromium. And now over here I have 4 oxygens, and so I'm going to produce 4 oxygens, and to do that you put a 2 here. So now you have a balanced chemical equation. 15 part C is a complete combustion, and it tells me gaseous, I just didn't write that part down, of C2H2. So I hope you remember the products of a complete combustion reaction, but I'm starting with C2H2. And in order to combust, it has to have oxygen gas. And the products of a complete combustion are always carbon dioxide and water. And remember, it is very important that they tell me it's complete combustion. And that tells me that there's enough oxygen to react with the carbons to produce carbon dioxide. If there's not enough oxygen, I get that elemental carbony soot and carbon monoxide, the poisonous gas. So now we're gonna balance the equation. It's our last equation to balance. I'm kind of tired of balancing these today. So here we have 2 carbons, 2 hydrogens, and 2 oxygens. We over here have 1 carbon, 2 hydrogens, and here's a mistake where a lot of people make, because oxygen is found in 2 products, so we have to remember to add those up. I cannot tell you how many times I see students not add hydrogen or the oxygen up and count it in both products. And so it's actually a 3 down here. So now let's balance it. We're gonna leave oxygen last because it's alone and it's easy to manipulate at the very end. And let's go ahead and do carbon first. And I see I made a mistake. I wrote 2 carbons. There's actually only 1 carbon. I want that to become 2 carbons because I have 2 carbons here. So I get that to 2 carbons by putting a 2 there, and that gives me 2 carbons, but that also changes that oxygen. And so 2 times 2 is here. I have 4 oxygens, but don't forget this oxygen down here. So it gives you a total of 5 oxygens. So now that your carbons are balanced out, your hydrogens are balanced out, you can balance out your oxygens. So we have 2, and we want to get it to a 5. And so I can say 2.5, like 2.5 times 2, equals 5. 2.5 times 2 equals 5. But the problem with that is I am left with a decimal, and it's not a whole number. So now you have to do the part where you multiply them all through by 2. And so you end up with a whole number. And so when you do that, and then all of this would multiply. And so you have your coefficients are a 2, a 5, a 4, and a 2. All right, last question. And so this one has 5 parts. I'll do the first 3 and I'll do the next 2 in a minute. And they actually give you these equations balanced, which makes me excited because I'm kind of tired of balancing equations today. But what you're going to do is we're looking to analyze these equations to tell what type of equation it is. So it can be either a formation. If you're in my class, I will gladly accept synthesis for that. Decomposition, single replacement, double displacement, complete combustion, or incomplete combustion. All the types of reactions we've talked about in this chapter. So on this first reaction, my first hint is I have one big compound, and I see that I am breaking it up into each of its parts. So anytime you have one compound and you're breaking it up, this is called a decomposition reaction. For part B, I see that I have a compound and I'm reacting it with oxygen. So that's a hint as to what type it is. And I'm producing carbon monoxide and water. And so this is a combustion reaction. I'm reacting this with oxygen, but because this is not producing CO2, it's producing carbon monoxide, that dangerous gas. This is an incomplete combustion reaction. For part C, I have 2 compounds and I'm producing 2 compounds. So I'm not necessarily taking a bunch of stuff and sticking it together. I'm not breaking something apart. And I'm not decomposing or combusting something. So I know that this is one of those displacement reactions. So you need to figure out, is it single displacement or is it double displacement? What is happening is, since we have, this is essentially a single element, chlorine is coming in and pushing the sulfur out and bonding to the hydrogen. If you'll see chlorine, it pushes the sulfur out and it takes its place. And since only really one of these atoms is pushing and changing places, this is called a single displacement reaction. So for D, they actually did not balance this reaction because I have 1 magnesium and it cannot possibly produce 3. But anyways, we have magnesium and nitrogen and we're combining it together to make magnesium nitride. And so since we're taking 2 things and we're combining them, this is a formation reaction. We're forming something. Part E, we are not forming something because I'm starting with 2 compounds and I'm forming 2 compounds. So I know it is not decomposition, formation, or a combustion reaction. So it must be one of those displacements. And so which type of displacement? Well, actually what is happening is these metals, the aluminum and the potassium, your metals here are switching partners. And so since both of them are switching partners, you have a double displacement reaction. Great job on the chapter 6 review questions.